Hey everybody, Blake here again with another part in this series about spacetime particles where we're trying to simplify physics using a medium that defines spacetime. In this particular episode, we're going to be looking at the distortions that spacetime particles could create due to density and flow. Okay, for this episode, we're going to review gravitational lensing and measurement methods. Then we're going to look into what I'm calling a two-part special relativity. We'll explain what that is. We'll look into then various different distortions due to spacetime particles, such as density, flow, a spiraling galaxy, and then what I'm calling spacetime particle blobs. And remember, the goal with this one is to demonstrate that we can create other optical distortions without adding huge amount of magical mass. So if the only tool that we have available is a hammer, everything looks like a nail. And that's the same thing with dark matter. If our only tool to solving optical distortions is by adding mass, then everything we see is going to look like dark matter. And our goal here is just to give some other options and say that maybe, just willy-nilly adding mass all the time isn't the best answer. Right now we're going to talk about gravitational lensing very quickly. So gravitational lensing is when very distant objects are optically distorted due to mass in between us and the source. And so this can be used to magnify images to give us a little better resolution. It can also be a way for us to estimate how much mass is between us and the object we're looking at. So it's a very useful phenomenon, assuming we understand the physics very well. Typically, we're going to be looking at this with some sort of instrument, and some of them here are listed below, just so we can kind of get an idea of what kind of resolutions we're going to need to target for something that's actually measurable. And that's just for the later analysis. But JWST is going to have a resolution about 0.1 arc seconds. An arc second is already very small, so this is small. And now we get to the extremely large telescope, and these are going to be ground-based. And we're looking at 1 to 3 milliarc seconds, which is crazy. The Chara array is even smaller than that, and then the Event Horizon Telescope is, I don't even know how to quantify how small that is, but it is beyond teeny weeny. Anyway, so just keep these numbers in mind when we're talking about light deflections later, because we're going to, if I can recreate something that's not within the range, then it doesn't matter. We have to be able to recreate distortions that are on the range as something measurable for it to be meaningful. So there's strong gravitational lensing, which is very obvious, right? Optical distortion. So there's some sort of galaxy or mass in the center here, and this light is actually coming from way farther behind the mass in the center, and it's basically getting curved around and getting distorted in this ring. So here's another example where we just have a couple images that are distorted and transposed, I guess. But you can see we got this dot and this little thing, and this dot, so it's mirrored over this. We have the same kind of image here, the dot and this little thing, and that's just, it's going to be bent according to whatever gravitational lens is in between us. And so this is, example of strong lensing. Now weak lensing is where you have not necessarily one large lens that's distorting, but you could have a lot of little bit of mass on the way, and it's going to be more of a statistical effort. Right, so here's an image, right? Strong lensing, you're clearly distorting the image. Now, if you were to look at a weak source, you'd be saying, well, we have all these galaxies that we can see, but they are being slightly distorted. And now I don't know if I agree with this image. There's not going to be this void. I mean, there will be mass in the foreground that's distorting it, but we're not going to see anything like a black spot like this. We're going to see um, these shapes slightly distorted. And what makes this even harder is you can't say if that galaxy should be this shape or if it's on edge and it's more ellipsoid shaped. And so when you're trying to understand gravitational lensing, you're looking at the shapes of the galaxies without knowing what they should be to start with, and you're trying to estimate, well, what sort of distortions are statistically prevalent in all of these images that we're seeing. And so it's a very hard challenge, but we can just, with this kind of method, you can start to sense even smaller distortions than, something that's huge here. So then how we're going to be doing this analysis, we're going to be using a two-part special relativity. So relativity is due to two actions. Motion creates an inertial bubble, right? So we've seen this before. A spaceship's moving along and it's going to drag along space-time particles with it. Now, in order for this bubble to exist, it must slip past the medium that's not moving. And in order to support this, the pressure increase that's going to be created, the density inside here is going to be increased. So density outside in the stationary medium is going to be rho naught, whereas the density inside is going to be greater. Basically, relativity is the combination of doing the math to account for the moving frame, but also the time dilation and distortions created when the density inside the inertial frame is increased. Now, some things to think about is that Einstein would have said, no matter what, whenever you're moving, we have to apply the same corrections. But that is now no longer the case. Let's just say that we have a boundary here. One person's standing on this side, and one person, and on this side we have a velocity where the medium is actually moving. So velocity m. And so now we have another person on this side, and they can have two clocks. What we're interested in order to calculate the time dilation is this person's velocity relative to the moving medium, not necessarily relative to the person that's in a non-moving medium, right? If this person is stationary, if the delta V equals 0, then this person is going to be moving relative to this medium. And so they're going to have to they're going to have their own inertial bubble, and this is going to be an increased density here. And so delta V equals 0, we do get whereas if this person was moving with the frame, if they had, so delta V would be equal to Vm. They're not moving with respect to right. So if this person is moving at velocity Vm, then we're going to not actually have any time dilation between them, even though they have different velocities. And this is important when we're going to be looking at galaxies later, but let's look at the next example. So there is the Ehrenfest paradox, where they were saying that if there's a rigid disk that could survive the relativistic speeds without shredding or disintegrating, there would be a Lorentz contraction along its circumference. So this would be our stationary rulers, but if this bit is rotating, then there would be a Lorentz contraction, and so the distance along here would look to be shrunk. But because it's a circumference, we can't really shrink the circumference without causing other negative effects to compensate. And so there is this paradox where we kind of get two conflicting issues. Now, what I'm trying to say is that any piece on this disk is going to be rotating in a circle. And this is going to be following the piece in front of it, and so on, until you get this complete loop where you always have material following material that's already rotating. Now, because you have this continuous loop, there is not going to be an instance where that mass is going to need to create some sort of inertial sphere condition. And so basically, you're not going to get a state where you need to create an increased density in space-time particles. So what I would argue is that in this disk, there's going to be no time dilation and no relativistic properties of the mass and energy or the time dilation or distance. So basically, it's going to be a disk that you rotate, and you're not going to have this paradox situation simply because you're not going to create this higher density configuration of space-time particles as this thing is rotating, because there's nothing to increase that pressure. So now let's look at distortions due to density of space-time particles, and this is basically just general relativity to start, but we're going to start somewhere easy. Okay, so we're going to be using this equation for this initial analysis, and we're just going to look at a couple situations here. But we have the light is going to be originating at this point. Red is going to have density n equals 1. Violet is going to be density or n equals 2. And we're going to see that as light hits the higher density, it's going to be deflected, and then it's going to be straightened out. And it is as you'd expect. Now, one thing to appreciate here is that we have, we start at this angle, we get deflected a certain amount, and then once we come out the other end, we return to the same angle. Now, something that's interesting with this kind of thing, analysis, is that it doesn't matter if it's a smooth transition from one end to the other, because it's always going to be conserved, right? So we're going to start at this angle here. We're going to slowly be deflected to our peak density of 2, and then we're going to return back to our expected. And so the same thing, we could sweep this, but in this one, we're going to do a time, like we're going to fire 2 little probes, and we can see how fast the light's going to be traveling. Now we can do the same thing with values for gamma and potential, but we're going to be using this equation. And if you notice that I had an n squared term in my equations, which then resolves to this, one of the things that's used when you're doing weak gravitational lensing, we'll do some assumptions, and they kind of come up with a very similar parameter here. So what I've done here, I do not think is novel by any means. So, but it's just what I've been using. Now, if we want to understand the deflection of light coming from a straight, light moving at a straight path to start, we can use this equation that Einstein developed. So this is an approximation, and so it's not perfect, but it is really good, as long as we're not doing too high a mass situations. And if you calculate this with the properties of a ray just glancing by the sun, you can get this answer. And I updated my simulation to clean some stuff and be a little bit more efficient. And I am pretty close to the same value there. Now later, I actually think I skipped at this one, but we're going to be looking at this later. Um, when we're trying to study the Milky Way and its more accurate density distribution, we're going to be using this equation. I think it's valid, um, but I'd like to confirm that a little bit more. So anyways, but this is just basically the gamma with respect to the potential instead of with respect to some given mass distribution or point source. I guess this would be a point source potential. Okay, so moving on. Now we're going to start looking at distortions due to flow. We kind of run into a couple new things when we're looking at the flow, um, distortions due to flow. So we're starting very high just so the distortions are very visible to start, but that is a third of the speed of light, and that's probably not something that we're going to experience when we're observing things, but maybe it is. I cannot say for certain, and there's no reason that it would be that high. But again, it's just nice to look at. So when light is coming in at this angle, it's going to be deflected according to our other equations for the aberration of light. Now, the one thing that we need to start to account is that light is going to be transported because it's now moving in this medium, and the medium is now moving, carrying the light, right? So this is looking at the light without advection, and now we're going to basically have advection. So as the light is moving in, it's going to be, the angle is going to change, but it's going to be carried along with the medium. And so we get this, what we would actually observe is an angle that is closer to the straight line of the non-distorted light. And one of the bigger, maybe not an issue, but one thing that we now run into is that we don't have this same nice conservation of angle coming in and out when flow of space-time particles. And so we have to be a little bit more careful with how we're doing this analysis. And we're just going to look at the consequences of these angle shifts. So we have a little bit of, maybe it's not even applicable to this conversation, but maybe somebody will find it interesting somewhere. Another interesting thing is that we can look at how fast the light seems to be moving, and this is with advection, right? So the light itself is going to be moving at c in that medium, but from a stationary perspective, light's going to be advecting, and so its velocity is not going to be c necessarily. So when we have a steep angle, it's going to look like it's slowing down, as you can see here. This is the straight line. And when we're going into the flow, it's actually going to speed up. Something kind of interesting. But now what I'm curious is, so at one angle, we're speeding up. At another angle, we're slowing down. And if we go back here, it's very interesting that this line is almost perfectly straight, right? So what does it mean if we have a zero angle change condition? So typically, tan Vy prime over Vx prime, and we're going to Well, yeah. So, and then if we're actually interested in the angle of deflection, we would be dealing with something like this. Now, remember that in this case, when we don't have any sort of other like assumed parameters, Vy prime, even though it's on the same side, the top of Vy, these two do not equal. However, we are going to be looking at the case when they are equal because we're interested in a special case. So Vy prime equals Vy and Vx. Right? So we're interested in whenever this deflection is going to be equal to the inverse of not the inverse, but the negative of the, the component that it's initially starting at. And so, right, so then the condition for this to be true is as long as Vx is equal to a half of V, the velocity of the flow. And then just Vx is just cosine, speed of light cosine. Now, something interesting there is before I showed that the velocity, the apparent velocity of the advected light, so that would be C prime, is going to differ based off of the angle, incoming angle. However, in this condition, let's look at what that's going to be. So V, now we have V, that's why Vx prime plus V, right? We're looking at the speed of light in the movie or in the stationary frame, and so we have to add the velocity here. This is going to be squared. And just to clarify up here, we have basically V, that's this component, plus the velocity here, and we're interested in this, which is just Vx. Right, and so that's basically what we get here is plus Vx prime plus V, and that is just minus Vx. And so that's where we get this up here. And so when we're continuing this calculation, Vy prime is just Vy. Right, and so the negative here, so then Vx prime is just going to be over here. Vx prime is equal to Vx minus V, right? So Vx minus V plus V squared. Well, those cancel, and basically C prime. Oops. That's why I keep doing that. And equals C. So when you have this zero change condition, your apparent velocity of light is going to be C and non-changed as it passes through the medium. Let's just look at this in just a little bit more detail before we're moving on. Now, what I'm doing here is I'm basically passing through light through some number of passes, and one pass is going to be light here. This would be a flow, and that's one pass. And then if we had the flow here again, and then this would be two pass. So I'm just basically saying one pass is going from stationary medium to a flowing medium back to stationary, and then we will repeat that as the light gets distorted due to each pass. Now, for one pass, this is pretty fast, a third of the speed of light. Now, for one pass, you can see that there's nothing that really stands out. You have an increase of energy around 90 degrees. There's this line here that represents basically this condition. Well, I guess I should circle that. Right? So basically, the constant angle, the no change, is here and here. I just have them, we're looking at degrees on both sides, so that's just intersection of those two. Do not think that this peak on this curve intersects this line. It's close, but it is not equal. Now, if we do 5 passes, you can start to see basically the angle here is going to start to be compressed along this constant angle, and the energy change is just getting a little bit more pronounced. But as the angle over here goes through more passes, it's going to get everything basically gets shifted to that constant angle situation. And so then we're going to end up with something like this. Right, at some point, you're always going to be adding energy when you pass in more and more, as you go through more and more passes. So, that's something that's interesting. Basically, anytime you're using a medium to distort light, you're most likely going to be adding energy to it. Now, we were talking about advection, and there is this slight possibility that light could be advected, you know, as it's passing through a medium, and this movement of light, or this transportation of light, could create optical distortions. If we imagine a really large chunk of space-time particles moving along that's 10 kiloparsecs wide, moving at 200 kilometers per second, and this is kind of my default velocity for a moving medium, because right now we see galaxies moving at around 200 kilometers per second, so or rotating. And so it just seems like that's kind of at least on the order of something that's reasonable. But if we have a large medium moving, and that's pretty wide, we can expect that there'd be some sort of transportation of the light when it goes from one end to the other. Now, this is very small. We're talking fractions of a parsec, and if we're looking at something that's millions of parsecs away, this is going to be a very, very small angle that we'd be measuring. So it's not likely something that we're going to see in terms of distortions of just getting light transported through different mediums. Now, looking at, again, we're going a third the speed of light. And we're just going through basically, we're looking at this situation, right? So just basically a river of moving space-time particles. You can see here we do get a little bit of a distortion that would be different coming in and going out. But this is for a third of speed of light, so not really something that would be realistic, right? And so, however, if we look at 200 kilometers per second, just difference here is the difference of light entering the medium and exiting the medium, and it's going to take a slight angle change. And this is pretty small, something that would not be visible with JWST, but it could be visible with maybe the higher resolution instruments. So this is something, it's not super big, but it is something. And so we looked at the angular deflection due to, a solid strip of space-time particles moving. But just because I don't know what space-time is going to look like, we're going to just quickly review what does it look like if it's varying. And it turns out that it actually shifts it back in the other direction a little bit. And now remember, this is very path dependent. And so the results here depend on how small of the steps we're taking. And so it really does depend on how smooth. So this is just kind of um, overview of what might happen. Basically what happens is when you have a varying flow, that does actually return or reduce the deflection a little bit. You can see this is at a third the speed of light, and so I think before we are at 8,000 arc seconds, and now we're at 8, so it's quite a bit smaller. And so if we look at something at a more reasonable velocity, 200 kilometers per second, now we're getting back into something that it's not likely we're going to measure, but we do get a difference on the front and the back end of the angle sweep. But yeah, this is teeny, so not something we're probably measuring. Okay, so now let's actually just look at the distortions due to galaxies. Now, how I'm modeling this is I'm just taking 25 kilopascals as the radius of the galaxy, and I'm using this same velocity profile that we used in the last one for the flow of the medium. And this is basically the flow required to match, to overcome the velocity difference of what we're measuring and what we're predicting, right? And so it's 95 kilometers per second at the peak. And so basically you can see here is that 0 is red, and then as we're moving towards the edge, we're going to start approaching this purple violet value, which is closer to 95 kilometers per second. And then we're going to be using that potential that I showed you before for the gamma calculation. So when we are now, and then one last thing is we're basically taking straight rays and we're just going to scan this across to calculate the deflections. So that's why this is now in parsecs, because we're moving across the diameter of the galaxy. And if we look here, this red curve is the angular deflection purely due to the density, the gravitational effects. And this dashed line here, well, I guess it's not dashed, but the blue line here is due to the flow. And this is not that big. And again, we're just using deflection due to the Milky Way like galaxies. A lot of the time we see big gravitational lensing, it's due to a larger source of mass. I'm just interested in the data I have, and it can be kind of extrapolate to other situations. But you can see here that we get, something that's pretty small, measurable maybe, but small. Now, the interesting thing here isn't necessarily this value, and we're going to get to that in a couple slides. Now we can actually calculate the time lag due to the swirling galaxy, and I kind of made a bad assumption last time I was talking about it. I basically undervalued distance. These galaxies are, 100,000 light years in diameter, so it takes a lot of time to travel from one end to the next. And even with a flow of 90 kilometers per second, I kind of assumed that only on the outer edges you would get any measurable difference, but it adds up. Over a long period of time, it adds up, and it's not really a big deal to light, because light's moving for, a long time. But for us, these calculations are saying that we're going to get plus or minus 35 years in time difference from one end to the other. And so this is like something I saw from Van der Waals in his heretical physics, which I had mentioned, that has some interesting thoughts on it. But we're not looking at 1 to 3 years, but we're looking at, upwards to 35 years just for the Milky Way. Now, I don't know if this is a good thing or a bad thing. This really does extend some of these predictions out quite a bit, because I think prior to this, you'd expect only a few years difference between two images. Now, one thing that is to say, there are not a lot of confirmed double images of supernovas. And it also probably depends on what path it is through the galaxy. So, yeah, like I said, that's a big time difference for something that we would measure. And so probably, one of the biggest things that we could look at to determine whether this medium is flowing in the way that I've been talking about or not. So, yeah, something to think about here. Now, what basically falls off from, if you're looking at the time difference, well, what about the energy coming out the other end of the lens? Now, there's two things that we're dealing with when we're moving through a swirling galaxy, and one is the aberration of light due to the moving medium, and then the other one is just the redshift due to gravitational effects. So we'd expect that the redshift or the Doppler shift due to gravitational effects would be basically the same coming in and going out, which we kind of see. So the black line is just gamma. And so this little curve here is purely due to the density, the mass of the galaxy. And then there's a Doppler effect due to the aberration of light, or due to the moving medium. And essentially what I'm plotting here is the Doppler correction -1, just because we're interested in the difference from 1, not necessarily 1. So you can see that we basically get this offset as we're moving through the medium, and then it kind of drops back down. So there's probably no redshift that we would be measuring, at least for moving through like a Milky Way sized galaxy, because the difference between the purely gravitational and the gravitational flow is probably very small, as we're already looking at a small value. I'm not sure what we're capable of measuring in terms of Doppler shifts, but this seems very small. Now, one thing that is interesting is that we do get this. I mean, it's still a very small Doppler shift, but we do get a Doppler shift inside of the galaxy. So again, but I don't know if that's something you can measure if you're from, the sun or from our solar system. Everything would be shifted appropriately. So, like, I'm not sure we could get anything out of this, but something to think about on that. Now, what I had mentioned before is that the angle difference created by a swirling galaxy and a non-swirling galaxy is very small. However, like I said before, when you only have a hammer that is mass, you're going to throw mass at everything. So now what I'm looking at is, if we use this equation, which I showed before, and we come up with this other equation, the mass of somebody that only has dark matter to solve the problem with, we can basically calculate the mass needed here to create the same deflection. So I'm looking at the change of angle due to a rotating galaxy versus purely just being deflected by the mass of the galaxy. And then I'm looking at what would be the apparent amount of mass due to a point source at the center. Now, that might not be super accurate, because usually they have masses distributed out, like smeared over, some sort of sphere. But just to kind of get an idea. And so what I can show here is that this is the dark matter ratio to the galaxy ratio, and the galaxy, it was kind of a light galaxy. Oh, I had mentioned it. And that's this point, that's value up here that I'm just using as a rough simulation value. And so what this is showing is that you're actually in order to create the same deflection with a point mass, you're almost doubling the amount of mass in the galaxy. And so that's not quite as ambitious as dark matter models with the 5 times or 6 times, whatever it is now, but it is something that in a very mild case, we can show, and especially right at the wings, which is kind of interesting, is that we're generating this kind of fake mass signal. And now this is just a curve of one of the models I've used before of the mass of the mass in the Milky Way, dark matter mass, and we get this slow increase to a higher increase, and then it kind of keeps going up, but that's because we're doing the total mass inside of a boundary, and once you've kind of summed up something inside, it never goes away. So we would expect some sort of asymptotic behavior here. Whereas this would say you have mass, 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 but then you've gone outside that slip condition. And so then there's no apparent mass once you get to a certain range outside the galaxy. Some just food for thought. Now, just for giggles, I want to look at what if we were to increase the velocity of the rotating galaxy by a factor of 2. We get a bigger deflection angle, and now we've created a much larger apparent dark matter need. We're at 3 times the mass of the galaxy that we're simulating here, and so it's quite a large effect. So if we have a little bit of an error in the velocity of our galaxy, we get quite a bit more. We would have an error of mass estimate here. And again, just for even more fun, if that's what is fun to you, we're going to do 3 times velocity. And now we're getting, half an arc second and almost 7 times the amount of mass to simulate that same deflection. I wanted to talk about Einstein crosses, but I was worried that was going to create a little bit too much distraction. And so I'm going to do kind of a couple parts to this in addition to what we're covering here. But mostly here, I'm just interested in, can we create Einstein crosses with previous tools, or do we need to, would Einstein crosses be easier to create with a flow type parameter to vary, as I've been showing? And then another thing that I want to look at is what the distortions of light would be due to a galaxy. Like if we're looking at this side, this is an eyeball and some sort of source over here. Right, we've been looking at this direction before. And so I'm curious is what kind of distortions we're going to expect when we're looking at the top of a galaxy. And so the problem with this is now we're getting into a 3-dimensional simulation, which isn't too hard. It's just something I have to add. So I'm going to do this again as maybe an add-on to this current study that we're looking at. But one thing that might actually happen is if you imagine that we have some sort of rod, the light is going to be probably twisted at the edges, and so you would expect the light to be twisted here. So then what are we going to see over here? Probably, I think it gets twisted in the opposite direction you think, but something that's going to be, expanded and stretched. So that's kind of roughly my prediction. I'm not sure if I'll be right, but we'll study this and see what that looks like later. Now, I want to move on, finish this last little study with another thing that I'm calling STP Blobs, or Spacetime Particle Blobs. And what basically this is when you have 2 galaxies, this is their velocity, and they're colliding. if there's medium that's swirling, you can like make a rough assumption that the mixing isn't going to be, the slip condition is going to kind of be in the center, and there might be a situation where perhaps the flow is getting accelerated and then ejected. So the medium that's swirling around the galaxy is going to be shot out in what I'm calling these STP blobs. So these are going to be moving out away. Now, what would these look like? We talk about like galaxies like the bullet clusters and stuff ejecting dark matter halos or whatever that create distortions of light. So this would be kind of the similar phenomenon, but this is already inherent with the galaxies and it's not any extra mass needed. And so I want to just look at, are we going to see any sort of distortions due to these blobs? Now, we did a moving river before, and that was like a constant flow of like a rectangular flow, and I changed the angle and we saw some deflection. This is different where I'm just scanning again over the diameter of this blob. And so the values are a little different, but you can see we get very little deflection here, which is probably likely something that won't be measured, but maybe with the higher, the higher resolution ground-based telescopes. However, what if those blobs are not accurate? What if, in reality, as these blobs are created, they are going to kind of slam into the medium that's not moving, right? So this would be density equal to, let me write that down in red. So this would be, rho naught, and this would likely be rho naught or something. But now, as this blob is now interacting with the stationary medium, there's going to be kind of this resistance of this blob going through this medium. And so there's going to be kind of pressure down on the blob, and that pressure is going to kind of get focused and compress and act as a compressing force on this blob. And so what I'm saying is that once this blob is ejected from the galaxy, the density here is going to be greater than the density of the background. And so I'm going to say that this same density is going to be proportional to, Einstein's equations for gamma. And well, the density, remember the density is, it's not a 1-to-1, but it's a cubed factor because density is volume and the gamma is a, one-dimensional adjustment. But, and that was, something like I wrote before. But anyway, this is going to be just due to Einstein's calculations. So now, essentially, we get two interesting ways to look at this. This is a blob that has a diameter of 5 kiloparsecs. It's moving at 200 kilometers per second. And the density that we're seeing here is increased due to this velocity. Now, we're going to get increase in density on the inside, and that could probably be uniform, I'm not sure. But we're going to get some sort of reaction on the outside. So the density of the space-time particles as this moves through is going to be increased. So that's what we're seeing here. We're seeing a high density here, which is violet, which is all just, it's so small relative to 1 that I didn't have enough digits here, but there's going to be a smooth transition from high density to low density as it moves away. And this is falling off with kind of with our gravitational laws, and so it is pretty smooth. But you can see here that we're starting to deflect light pretty considerably due to this blob, 0.15. And if we do kind of the same thing as we did before, we can look at what the amount of mass at the center would be needed to require that same deflection. And we've basically just created a 5 kilopascal, I want to say kilopascals, a 5 kiloparsec blob moving at 200 kilometers per second basically simulates almost a whole galaxy worth of mass um, that is actually not there. And this is just the time delay just for giggles, I guess, but there's not going to be a huge time delay as we move through this blob. Now, this fall off here, there's no reason that it should fall off like this, because the fall off here is assuming there's actually mass in the center. I'm saying that this is due to a blob moving through a medium. So now if you imagine that this blob is moving through a medium, the density that's increasing from the middle, due to this interaction is not going to fall off like Einstein or Newton had said. It's going to fall off due to some sort of flow parameter. And what's interesting is when you have a sharper gradient of change in density, you actually get a much larger deflection in angle of the light rays. And so we're going to do the same thing here. We're just looking at the deflection here. We're starting to get some peaks, right at the edges where there's the highest transition of density. And so right around the perimeter of this moving blob, we're going to see almost 1.5 times the mass of a galaxy needed to simulate the same deflection. So we're going to have to figure out, put a lot more thought into how this is falling off. And, hopefully this will fall out when we start to look into the details of the physics a lot more. But just with these blobs, we can show a lot of deflection, and that's all that I want to cover on these. Okay, so now we're just going to review and wrap up. So to review, a moving medium can create optical distortions. A spiral galaxy can show a considerable amount of additional distortions, especially towards the outer edges, which is kind of very interesting. And we can also use spacetime particle blobs released from galaxy collisions to also create large distortions. Now, this is just a few examples of how we can basically distort light rays, the paths of light, on our way to us. And it all is possible without adding huge amounts of dark matter or dark mass in order to create gravitational lensing. So this is just some tools that maybe somebody can use down the road, or we can start to investigate more, but I will definitely be doing more digging later. And I hope that this was kind of an interesting overview. So our next steps, I really want to do, might be add-ons to this presentation would be Einstein crosses and looking at the galaxy distortions due to different positions. I did not, for all of the analysis here, I just assumed the galaxy Milky Way was a point mass. And so when I'm looking at the actual distortions due to Milky Way, I'm going to have to use the previous potentials we studied before. They don't change the values too much, but it does change it a little bit. Just requires a little bit more careful processing. Something else I would like to talk about is the high gravity consequences of space-time and particles. So before I had mentioned that there might be some discrepancies with general relativity when the gravitational masses get very large. I wasn't sure how I was going to test this, but it just so happened that I stumbled on a really easy test scenario that showed that there indeed was a discrepancy between the model that I'm using and general relativity. I don't know if this is good or bad, but there's certainly, I guess it wasn't surprising. And this has to do with the fact that space-time particles is assuming more of a symmetric distortion of the medium as mass increases, whereas general relativity assumes that there's only distortions in the radial direction. So I want to go into that. I want to dig in, make sure that that's actually real, or at least a thing that we can consider talking about. And then back to the double slit experiment, I would like to try to simulate why we're what is creating the wiggles of the de Broglie wavelength like we've talked before. So anyway, thanks for listening. I hope this was interesting. If you have any thoughts or comments, please put them in the comments below, and like and subscribe or something. All right, until next time.